Okay, cool. I'm going to kickstart the presentation. Well, hey everybody. My name is Alex Merced. I'm a senior tech evangelist here at Dremio. And what I'm going to talk about today is the who, the what, and the why of data lakehouse table formats. A really interesting topic, and it's a topic that I guess whose time has come. It's really been a very big talk, especially when you're talking about really like large data platforms handling petabytes of data. The whole concept of a data lakehouse and how you're going to store that data for data lakehouse has really become sort of key to the migration to this pattern. But again, my name is Alex Merced. You can follow me on Twitter at amdata_lakehouse. And then here is a link to download the slides. So basically, if you scan this QR code, because there's gonna be a lot of QR codes during my presentation, this will get you to the whole slide deck so that we have all the links readily available. But yeah, so basically that'll be there, and I'll share it again at the end. But yeah, so that's there for you to get all the slides, and they'll take you to a folder with not only the slides for this presentation, but for other presentations I do. So feel free to look at those as well. But a little bit about sort of who I am and who I'm with. Again, I'm a senior developer evangelist for Dremio, and what Dremio is, it's the long-winded way of putting it, the unified lakehouse platform for self-service analytics. But the bottom line, what it is that it makes implementing a data lakehouse really easy. Basically, in three tiers of services. So what we do is we have a unified analytics layer, which allows you to connect data from across many sources. Okay, so that'd be terms probably heard like data federation, data virtualization. So you can connect to your MongoDB, your Postgres, your SQL Server, all sorts of different databases, data warehouses. You can connect to Snowflake, you can connect to Redshift, you can connect to Synapse, you can connect to your data lake on AWS or ADLS, and be able to query all those data sources from one layer, curate joins and views on that data from one layer, and govern all that data from one layer. So we have that unified analytics tier. We have our SQL query engine. So basically, you can run SQL and process SQL queries across all those sources using Dremio in a very performant way. Some of the benchmarks I've seen recently, I mean, very recently, I don't think this includes the newest version that's about to come out, are about equivalent speed to Snowflake. I think she may be a tiny bit faster. I think DB SQL is where it's like equivalent. But basically we have, but again, you're basically getting data warehouse speeds, but directly on your data lake. And that's very much thanks to our acceleration technology, which is called Reflections. I have a whole separate presentation on that to talk about another time. And also Apache Arrow, which is another really great open source technology, which actually started out as Dremio's in-memory format in its early days. And then our third is our lakehouse management tier of services, where basically bottom line is, if you want a lakehouse, that's great. There's a lot of benefits to lakehouses we'll discuss. But one of the things we like about data warehouses is they just kind of take care of themselves. So if people are going to migrate to a data lakehouse, it should be easy to use like a data warehouse. And that's where the data lakehouse management piece comes in, where we're managing your tables. We're making sure that we're optimizing everything kind of behind the scenes, so that way you don't have to think about it. Okay, and the cool thing about Dremio that makes it a little bit different than things like Snowflake and Databricks is that we can be deployed not just in the cloud through our cloud managed service, but also on-prem using our self-managed edition. And we're able to connect to on-prem and cloud sources, allowing you to truly sort of unify your data anywhere and truly implement that data lakehouse type architecture, whether you're an on-prem, in the cloud, or hybrid type environment. But that's who we are. And again, I'm also one of the co-authors of Apache Iceberg, the definitive guide. This should be actually officially being released next week. Okay, so yay, that was a journey. But you can get a free copy of this book. All you have to do is actually register for our annual conference. That's the Subsurface Lakehouse Conference. It's free to register, so basically no cost. It's online or in person in New York City. So if anyone watching happens to be in New York City, you can attend there. It's May 2nd and 3rd. And the URL to register is right there, dremio.com/subsurface. It's free. Just by registering, you'll get a PDF of the final copy of the Apache Iceberg book that covers a lot of the stuff I'll talk about today, but in much grander detail. And again, I'm a now senior tech evangelist at Dremio. That title change just happened a week ago. So that's that. And I'm also the host of a lot of different data podcasts because I like to talk about data. So here you can find all the different podcasts that I'm a host of, all available on iTunes, Stitcher, Google Play, wherever you look for podcasts. And now on with the featured presentation. Now, bottom line, to really appreciate what a data lakehouse is, because we need to know what a data lakehouse is to know what a data lakehouse table format is, we need to talk about traditional data systems, like what came before, what still exists, what's the traditional way of doing things. And that's using traditional sort of siloed data systems, which are often great to a point. These are like databases and data warehouses. Okay. And in databases and data warehouses, the great things about these types of software is that they abstract many things so we don't have to think about them. We can focus on sort of like, hey, what is our data? How do we going to model our data? I don't have to, when I'm using Postgres, I'm not thinking too hard about how that data is stored on the hard drive. Okay. Postgres figures that out for me. Okay. Or Snowflake, if we're talking about a data warehouse. A table format. Okay. So essentially, how do we know that certain data that's stored is this table A versus table B? Well, under the hood, there has to be some sort of system to kind of determine that. Cataloging. How do we know that table A, table B, table C, table D, how do we know the variety of tables that exist within our system? Well, again, there has to be a way of doing that, but that's all abstracted away. I don't have to think about how that works when I'm using a database or a data warehouse. And finally, a way of parsing my SQL, turning that SQL into a query plan, and then executing that query plan. Again, all this stuff is abstracted away from me, not generally the things that I have to really focus on, so that way I can just focusing on manage the actual data itself. Whether it's in a traditional database, which is typically going to be a more row-based type structure for basically transactional type queries, or in a data warehouse, traditionally probably a more columnar type data structure for more analytical type queries. Now, this is all fine and good, but the problem is, because all this stuff is abstracted away, if I want to use two databases, so if I want to use Postgres and SQL Server, well, they can't really talk to each other. Okay, so I have to either, like, if I have two tables that I want to join between the two, I have to either copy the Postgres table to SQL Server or copy the SQL Server over to Postgres, which can be complicated, costly, and, well, a lot of work. Okay, so oftentimes when if you need multiple data systems, because maybe certain data systems are better for certain use cases, it makes it really hard. You end up having lots of copies of the data that are kind of hard to manage, can lead to regulatory problems when you have accidentally exposed PII because you have so many copies, you forgot to lock one down. So ideally, once you start getting to really, really large scales, you may not want to have so many copies of the data. You may want to have a single copy of the data. And there is sort of an open access layer for data. There's something called the data lake, where basically we just store all our data in this big dumping ground, essentially a giant distributed hard drive, like a Hadoop or a AWS S3 object storage. And we say, hey, here's a bunch of data files. This could be unstructured data, like audio recordings, emails, could be structured data, maybe certain like Parquet files, CSV files, semi-structured data, and JSON files. All just dump all the data there. Okay, and that's good. And there are tools for querying that data, so we can now just work with all the data in one place. So we have tools like Dremio that are really useful for querying your data lake, or AWS Athena. Okay, those are all fine and good, but generally it's read-only. Like generally, hey, I'm querying the data, but I'm not creating tables. I'm not updating tables. There's a lot of workloads I can't do, so I still need the databases and the data warehouses. But if we take a look at this, the reason why that's the case is because we're missing a couple layers here. So what if we introduced those layers? Well, that's where we get into something called a data lake house. Okay, where we take that storage layer, which could be, again, Hadoop, could be AWS S3, ADLS, choose your favorite storage layer. You take your traditional data lake computing tools, so something like a Dremio or AWS Athena, but then we're going to add a way to recognize the individual tables on that storage, a table format. Okay, and that's going to be the main crux of our talk today. Also, we need a way to sort of be able to recognize all the unique tables that we have, a catalog. So there's another open source technology called Nessie that I do a lot of talks on that covers that piece of the story. But once we introduce these pieces, you now have all the layers to have the ability to do all the things that you're used to on a database or data warehouse. I can have asset guarantees when I'm writing and reading, and basically be able to also do a bunch of other cool things like schema evolution, partition evolution for certain formats, a lot of really cool stuff. Okay, but that's sort of the idea of a data lakehouse. The idea is we take all the pieces that make up a database or a data warehouse, but instead of putting them into one software system, each of them become their own piece that we can assemble together in a modular fashion, essentially a deconstructed data warehouse. So there are three sort of main table formats that are sort of vying to be the standard for how we represent data tables in data lakehouses. Now, again, all three of these formats at the end of the day are just standards for how the metadata should look like. The data is pretty standard. That the standard generally is that the actual data, like the actual like rows of data and columns of data, are stored in Parquet. So generally, you're still going to have Parquet files as the main way you store data in your data lake for high performance analytics. But the thing is that big data sets, they're not just one Parquet file. They might be thousands of Parquet files or hundreds of thousands of Parquet files. So you need a layer of metadata, so that way a tool like Dremio or other query engines can sit there and say, hey, this 1,000 Parquet files are one single table, okay, and be able to understand it within those semantics. Okay, so each of these formats do it in a different way. Now, the first format we're going to talk about is Apache Iceberg. So here's Apache Iceberg's story. And the way Apache Iceberg works is that it all starts off with a catalog. Okay, so this could be, it doesn't really matter which one it is, but right now there's Nessie, AWS Glue, there's a REST catalog. The point is it's going to be some sort of mechanism that actually has a list of tables. It could actually even be other databases. That's the JDBC catalog. But the idea is that it'll have a list of table A, table B, table C, table D. And what it does, all that reference has is a storage address to where the metadata is stored. So in this case, if I were Dremio trying to query an Iceberg table, I would first go to this catalog and say, hey, I'm looking for table A. And then the catalog would come back to me and say, hey, that's the S3 location for the newest metadata file is here. And then Dremio would then go to S3, get that metadata file, which is usually a file called metadata.json, and read that file. And that file is going to be where Dremio can discover the schema for the table, how the table is partitioned, okay, into sort of subtables. Basically what is the snapshot history of the table, all these sort of high level things. Okay, so now it has a better understanding of the table, and then it's going to identify which version of the table, because we're actually tracking the history of the table. Okay, so it'll say, hey, I want to scan the current snapshot, and each snapshot is tracked by what's called a manifest list, and the manifest list will be a list of manifests. This is where the terminology gets a little funky. So basically, Dremio will look at the metadata.json, and the only reason it knows which one's the right one is because the catalog told it. And now it's going to say, hey, I want the latest snapshot, which points to the manifest list for that particular snapshot. Now, in the manifest list are a list of different manifests, and each manifest represents a group of data files. Usually, like each one represents at least one partition. Okay, so let's imagine that I have a table that's partitioned by month. Okay, so basically there might be one manifest for all the January 2024 data, and then another manifest that has all the files that include data for December 2023, and so forth and so forth and so forth. Okay, so what's going to happen is that at the manifest list level, we're going to take the aggregate stats of each manifest and put them in that manifest list. So I'll see, hey, this manifest covers partition values, like covers like between this timestamp and this timestamp, and so forth. And the cool thing about this is that if my table is partitioned, I can now at this point take a look at those partition values in the metadata in the manifest list and say, hey, this manifest doesn't matter. This one doesn't matter. This one doesn't matter. This way, instead of me scanning all 1,000 Parquet files to do a query, I may scan a lot less. And then once I get rid of all the manifests that aren't relevant to my query, I can then now scan the remaining manifests. And the manifests actually have the individual listings of each Parquet file with stats on each file. So you'll say, hey, this file represents values between this and this range, this and this range. So now I can go down each file and say, hey, does this file make sense for my query? Nope, throw it out. Does this file make sense for my query? Nope, throw it out. And the idea is I could have a table that's 1,000 Parquet files, but after going through the metadata, I end up only scanning 3. And since I'm only scanning 3 files, that query is going to be a lot faster than if I scanned all 1,000 files. Okay, so basically, Iceberg goes a long way, or actually all these formats, through the ability to skip data files because of the metadata, goes a long way in being able to get that data warehouse-like performance on the data lake. Okay, so and essentially once you do that, I then identify the files I need to scan those files, and then process my query. Okay, and then then the query engine takes it from there. Okay, so essentially with the these table formats do is they allow the query engine to know, hey, these are the specific files I need to scan to complete this query. And Iceberg does it through this metadata tree, which has some really neat benefits because keep in mind for later that Iceberg, basically how the table is partitioned, how the table's this actual schema is all figured out up front. Okay, so even before we start looking at individual files, we know what the structure at a high level of the table is, which will allow for more robust sort of evolution features. Okay, now if I were to like just do a raw Iceberg table on storage, usually you would see something like this. You're going to see like two folders. You'll see like a data folder. That's going to be just where the actual Parquet files are stored. And then you'll see like a metadata folder, and that's where all the metadata files would be stored. So you'd see like your different metadata.jsons. You see all the manifest lists, which each would start with like a name like snap because they represent a snapshot. And then you see all the other manifests, which would just be names that just gibberish names. Cool. So that's like the architecture of Apache Iceberg. Okay, and then again, this just reiterates what I said earlier. But another format is Apache Hudi. And another important thing to kind of keep in mind as we go through these formats is sort of their history. So Apache Hudi was created at Uber, while Apache Iceberg was created at Netflix. Okay, so Netflix was trying to deal with huge giant data sets and being able to scan huge giant data sets very quickly. Uber, their problem was trying to deal with streaming ingestion and trying to handle lots of data coming in really quick and being able to query that data efficiently while being able to ingest that data really efficiently. Okay, so the structure of Hudi really focuses on trying to solve that streaming problem, while like Apache Iceberg's initial architecture really focused on trying to solve that sort of efficient read problem. It's much more sort of general use case focused. So Apache Hudi, focusing on streaming, really does everything through a timeline. So literally every time a transaction happens, the way each transaction is identified uniquely is through its like timestamp. Okay, so two transactions can't occupy the same moment. Okay, and that's how it makes sure that there's a clear history of how this table's changed, so that way you can always recreate the table at any particular time. Okay, and again, all three formats are going to have that time travel feature, where you'll be able to query historical versions of the table. And that's all because of the way they track their metadata. So Apache Hudi probably has like the most involved architecture. So basically the way it handles this, it does it through a lot of different files. And again, the benefit of having a lot of different files all over the place is that you're less likely to run issues in two transactions editing the same file. Okay, so essentially you'll have all your partition folders, so you'll have your table and all your Parquet files, but depending on how your Hudi table structured, it may do what's called a merge on read approach. Okay, so instead of rewriting the data file, so if I have a data file with like 1,000 records and I edit one of those records, usually these table formats all default to copy on write. So that means to edit that one record in that file of 1,000 records, it's going to rewrite the entire file. So I'm going to rewrite 1,000 records because I updated one. That can be really slow if you're doing a lot of updates and a lot of deletes. So all three formats have a way of doing what's called merge on read. Hudi had this first, but the basic idea is the way they do it is when I change sort of like one record, if I have merge on read enabled, instead of rewriting the entire data file, it creates what's called a log file. And the log file will track the changes. Okay, so each data file could have a bunch of log files that represent changes to records in that particular Parquet file. So then when you read the table, the query engine would then take that Parquet file and then reconcile all the different log files for that particular Parquet file. And that's how you would make sure you get an accurate version of the data. So yeah, so that's the story with like the data files. But then there's like this .hudi folder that's in there, and that's where all the metadata is. That's broken up into a couple different categories. There's a hudi.properties file. That's going to be where all the table properties are. Like, hey, is this a copy on write table? Is this a merge on read table? Stuff like that. Then there's the transaction logs. This is how Hudi tracks, where the actual, like, something happens. How do we know that what happens is, like, let's say a write comes in. We're writing some new records. first thing that's going to happen is that it's going to create a file with the timestamp. So you see here, like with the timestamp, and it's going to be called dot requested. So that means, hey, this basically claiming that, hey, this timestamp has been taken. So no other transaction can now claim this timestamp because there's already a requested file in here. The transaction's not done yet, but any transaction that comes in now needs to have a timestamp after this. Okay. And then once it actually starts doing the transaction, it'll rename the file to in flight. So then it'll be like dot in flight. And then once the transaction's complete, it'll gather a bunch of data summarizing the result and put that in a dot commit file. And that dot commit file then only summarizes the changes up to that point. So like, hey, these files were added, these files were subtracted, etc. And then that's kind of how it tracks the changing of the table. And then there's a metadata folder, which has basically a bunch of indexes to help in certain reading situations, because all the files are kind of, as you see here, like there's a bunch of log files I might have to like reconcile. There's all these like dot commit files that I need to reconcile. And then there's going to be all these indexes. These indexes are there to help, depending on the type of read you're doing and what kind of query you're running, to help speed things up a little bit. So there's like a metadata table that can be used for doing tables file skipping that has like metadata on each file, which an engine can then use to kind of say, hey, these files don't make sense for my query. You can do there's bloom filters, file listings, all sorts of different metadata that it can use to sort of then sit there and say, hey, these parts of the table I don't care about for this particular query. Again, a little bit less straightforward, but again, the idea was to have it sprawled out so that way you can handle that sort of really high speed streaming that Uber needed to handle. Okay, so here you can kind of see that all. So basically, a query comes in, or let's say again a write comes in. It establishes a timestamp. That timestamp then basically starts that whole requested in-flight commit cycle, and then each data file that gets written, as it changes, log files are written for the changes, assuming merge on read. Okay, if you're doing copy on write, then the data files would just be rewritten every time, and that goes for all formats. And then it would then use the file stats to do any kind of pruning. So again, if a query comes in, it would say, hey, I'm querying based on this timestamp. Figure out, hey, which files matter at that timestamp. Use the indexes to then sort of reduce which files I need to read, and then scan the files that are part of the scan. And then that's what the engine would do. Okay, so that's Apache Hudi. And again, the goal of all three of these formats is to provide the metadata, a universal form of the metadata. Because again, when you're using a database or a data warehouse, they all have metadata like this. They all have a structure like this, but it's exclusive to that tool. So other, basically Postgres wouldn't be able to just look at your SQL Server storage and know, hey, this table is that table, this table is that table, because they both understand those tables differently through a different structured metadata. The idea here is if the same stored data has a universally exposed metadata layer, then any tool can read those tables. So basically you have a storage of a bunch of tables that different tools can communicate with. And that's kind of the direction of things here. So Delta Lake is a third format. It's the only one of the three formats that isn't an Apache Foundation project, which is more, that's basically why that matters is just more like how, not whether the code is open source, like in the sense that you can see it, but also just as far as like who's running it. Basically, Apache has a lot of rules as far as like, hey, there can't be really one company that has like complete control over the format. It has to be, you have to have a lot of contributors across a lot of parts in the industry. It has to be very community oriented and very democratic in the way that the project evolves. Delta Lake definitely started out at Databricks. And again, Databricks was a company that's basically started out is you have the people who created Spark were like, okay, well, Spark's great, but people have to go like deploy Spark, and managing a Spark cluster can be a lot of work and get really complicated. So how about we provide a service that manages Spark for you? Okay, so basically you just can spin up a Spark cluster and do all that work you do with Spark really easily, and we'll even integrate notebooks so that way those notebooks you can just write your PySpark scripts pretty easily without having to do all that infrastructure setup. Okay, and this became really, really popular, especially in the AI ML space, where they use a lot of Spark and they use a lot of Python. But the thing is that basically Spark generally doesn't operate in a data warehouse; it operates on the lake. So they needed a way to be able to compete with like Snowflake on performance. they needed a way to understand data in the data lake that like tables, okay, that basically make it more like a data warehouse. Thus, Delta Lake gets created. And the approach they take with Delta Lake is they take a much more Git-like approach. So if you ever use Git to write code, when you make a Git commit, what you're tracking is these are the lines I got added, these are the lines I got subtracted. Okay. In this case, what a Delta commit looks like is these are the files that were added, these are the files that were subtracted. So which Parquet files have new data, and which Parquet files are no longer part of the table. Okay, and essentially each Delta log file is just that. It's just basically we've added these files, we've subtracted these files. Probably the simplest to understand out of the three. Although again, sometimes simple will preclude certain features. But basically that's how it works. And essentially what happened is that a query engine who wants to recreate a Delta log file, they would just sit there and say, hey, I want to query the table at a particular timestamp. It would just read every Delta log up to that timestamp and be able to recreate that table as it was at that particular time. Okay, and basically again, each format has its mechanism. In Apache Iceberg, you had a manifest list for each snapshot, so you would just find the right manifest list. In Apache Hudi, you would just use a timestamp and just process everything up to that timestamp. And in here, you have Delta log files, and each Delta log file has a timestamp associated with it, and it would just find what is the most closest Delta log file to your timestamp, and then process all the Delta log files before that and recreate the table. Now that's all fine and good, but what happens if you've made like thousands and thousands of changes? Now you have like thousands and thousands of Delta log files to iterate through. Okay, that's going to end up being a slow query because it's going to just take so long looping through those files, reading them just to construct the list of files that make up the table. Okay, so what they've done is they created a thing called a checkpoint file. So what you do is periodically, you're like, okay, well, let's just summarize the last 1,000 commits. So you create this checkpoint file, which will basically summarize where the data is at the end of this group of commits. So this way, instead of me having to read these 3 Delta log files one by one to recreate the table, I can just start with the checkpoint. This is just going to give me basically a summary of everything up to that point. And then I can just use the Delta logs to make changes to that going forward from the last checkpoint. So those are essentially the 2 different types of files in Delta Lake. There's checkpoints, and then there's Delta log files. And essentially everything is tracked through those 2 files. Okay, and yeah, those are sort of the 3 formats. And then again, when you take a look at Delta Lakes, if you ever make a Delta Lake table, which you can do pretty easily with like something like Polars if you want to test it out. Basically what you do is you see a folder, you'll see like all your data files and folders for partitions and things like that. And what you'll do is in there, you'll see a Delta log folder, and that's where you're going to find all these log files and checkpoint files. And that's where you'll see all that metadata is. So again, there's always a separation between metadata and data. Okay, the same, like just because the metadata standard changes, whether it's Iceberg, Delta, or Hudi, the underlying data doesn't change. They're just Parquet files. Okay, which is just a open source binary columnar table file format that's like really, really fast for analytical data. So that's all fine and good. And that's why you have like this new thing called the X table, which I'll talk about it. It comes up a little bit later. But basically, you can convert your metadata from one format to another without having to rewrite all the data files. Because at the end of the day, the data is the data. The table format's really just the metadata layer that sits on top of the data. It's basically what allows a tool like Dremio to better understand how to most efficiently scan the 1,000 files you already had. Okay, and then again, this just summarizes how that works. Again, we would just iterate through the checkpoints and log files to recreate the table. So now that we've seen what the 3 different formats are, so again, there's Apache Iceberg that started at Netflix, but now it's a community-run Apache project. We have Apache Hudi that started at Uber, but now is an Apache community-run Apache project. And then we have Delta Lake, which started at Databricks. It's technically a Linux Foundation project, but Databricks still pretty much controls the core project pretty heavily. But all 3 formats have ACID transactions. Okay, that means with all 3 of them, because of the way they structure their metadata and the different controls they put into place, you can do things that traditionally could only be done in a database or a data warehouse, being able to update transactions and be able to do like concurrent updates and concurrent deletes in a safe way that wouldn't result in inconsistent data. Being able to isolate those transactions, making sure that results of those transactions stick around. All that stuff is part of these formats, part of that specification, or enabled by that specification. All three formats have schema evolution. Okay, we take for granted when you're using like Postgres or Snowflake or something like that, and you sit there and say, hey, let me just change this column's name, or let me just go change this column from like an int to a big int or something like that. We take for granted what's actually going on under the hood, okay? Because there's a lot of constraints that have to happen to the actual way the data is stored underneath to optimize for that. So when you make those changes, a lot of stuff is going on under the hood to make it possible. So oftentimes with data lake table sets, because you weren't operating in one of these systems, you basically, the Parquet files you wrote were the Parquet files you wrote, and you couldn't just change the schema without rewriting the whole table. You just have to rewrite the data with the different schema, okay? Which is, when you talk about petabyte-sized tables, that gets kind of expensive. So that's no fun. But because the metadata tracks the schema, so we can actually see, hey, this is the schema we want to apply. It doesn't matter if the original Parquet file is different. Okay, the engine can know, hey, this is the desired schema, scan the data, and then coerce it to the current schema after the fact, making it where you don't have to rewrite every data file just because you added a column, you removed a column, you renamed a column, all that. So that's really, really cool. Okay. Efficient. So this is what I was talking about earlier with like merge on read. So again, there's copy on write, merge on read. Copy on write. One row changes in a file, you rewrite the whole file. Okay, basically, and the benefit of that is the read doesn't have to then reconcile it later, so the read's faster. But when you're worried about the write speed, so it's always those trade-offs between read and write. When you're worried about the write speed, then you rather have the write be faster and do less work, and then just do the extra work on the read. Especially for like streaming use cases. So all three of these do have a copy on write, merge on read distinction. Apache Iceberg, you can actually distinguish when to use merge on write and copy on read actually at a transactional level. So there's actually settings to say, hey, we'll do merge on read for like updates, but we'll do copy on write for deletes. Like you can get that granular with it. A Hudi, it's a table level setting. So you can say, hey, this table is either a merge on read table or a copy on write table. Delta Lake recently added this feature. It's referred to as deletion vectors. So basically what it does, it creates this structure called a deletion vector that tracks those changes to that single file and then reconciles it. But it's essentially merge on read. They just gave it a different name. Okay. So all three formats have that. So as you can see, most features, all three formats have. At the end of the day, like all three of them are trying to build a complete data system on the data lake. So generally one feature that one had and the other didn't, they've all kind of caught up because at the end of the day, those are all features that you generally want in your data system. But there are going to be a few unique things. Okay, then there's like all these formats also have optimization features. And here's where things get a little, like, I think when you read a lot of the literature, things get a little confusing here. Because people will talk about, hey, like this table has Z order. Well, the format doesn't sort itself. Like at the end of the day, the metadata is just metadata. They're just files, and the data files are just data files. So that has nothing necessarily to do with the format. But the question is, are there tools to help you optimize your data when you're using that format? And those tools can oftentimes help cluster your data, which means you might want to do it on a basic sort of one column, or a more complex sort like a Z order where you're equally weighting multiple columns, because maybe you generally query based on both fields. So nowadays, all three formats within their optimization tools do have the ability to do Z order. But there is a difference in how each table handles optimization. Okay, so like Hudi's pretty unique in the sense that their solution was to actually make it part of the project. So in the sense that when you're using Hudi, there's actually this separate tool called the Delta Streamer that you would run. So it'd be something you would separately deploy. It would be a separately running service. And then basically would do the ingestion. So you would point it to like a stream. It would handle the ingestion of the stream, but it would also concurrently be doing optimization of your data files. So essentially it's a separate process that just kind of manages all that. That's part of the open source project. It can be a little bit tricky to deploy and manage. That's generally like that's sort of not having to deal with that is generally one of the big benefits of working with a table like a company like One House, which is sort of the company that basically productized Apache Hudi. Like they're like, hey, you want to do Apache Hudi, we'll help you do that. That's their thing. Then there's Delta Lake. Delta Lake's approach to optimization, actually a lot of the services and features, and this is where it gets really messy in the documentation, is that there's like a really like thin line between sort of what's actually Delta Lake and what's Databricks. So a lot of times they'll say, hey, there's a new Delta Lake feature, but it's really something you can only do from the Databricks platform. So like a lot of things like being able to optimize your Delta Lake tables, oftentimes commands that are built into Databricks' fork of Spark. So yes, you have those features, but they're only usable from their platform. Sometimes they eventually, if they can, add them to Spark open source. So then it becomes a more open source like feature. But oftentimes that gets confusing because when you read the two sets of documentation, the Databricks sets of documentation and the Delta Lake documentation, there can be a lot of differences in sort of what you can and can't do that's oftentimes not made very clearly. So say like, for example, like deletion vectors, I think either still can't be used outside of Databricks or it's just about finally been added to OSS. And then there's also generated columns, which is another feature of Delta Lake, because those tools, those features aren't a feature of, they're not metadata features. They're not about how the metadata is tracked. They're about the way the compute engine handles the transaction. So again, it's going to be which engine implemented the feature. Now, Iceberg, its optimization, part of the open source side of the optimization is that it did make contributions to, it has a whole library for using open source Spark that has all that built in. So all the optimization you'd want to do on Iceberg tables. But one of the things about Iceberg, because it doesn't have like a built-in, it's very metadata centric. Like the Apache Iceberg project tries very, very hard to not build services and not rely on external services. Really try to build like a robust metadata layer that allows whatever tool you want to use to do the things you want. So what's been really interesting that's unique to Iceberg is that now there's a whole ecosystem of optimization tools. So while you can use open source Spark to do things like cluster your data and whatnot just fine with Apache Iceberg, now there's services like Dremio is in the Iceberg management game, Tabular, which is created by the founders of Iceberg, the original creators of Iceberg, is in the Iceberg table management game. Upsolver just got into the table management game. Snowflake's now in the Iceberg, the table management game, and more are being added every day. So everyone's like, okay, hey, this is a unique, because again, no one's really, Iceberg doesn't have like anyone who's like, there's no company that controls Iceberg. So basically everyone's like, hey, this is a good space where it's agnostic and everyone wants to kind of be part of that space. So you got a lot of options, which is unique in the Iceberg environment. Well, generally, you generally have one main option with the other two. Okay. Another aspect where there's a lot of difference is lakehouse versioning. So what I'm talking about here is one of the things that are starting to become more and more of a thing with data is basically having like Git-like semantics when you work with your data. Okay. So what I mean by that is being able to have the benefits of like Git. So what do I get when I use Git? I can isolate the work on my code without affecting other people's work. Okay, which is great for collaboration, great for testing. So I can test my work out before I merge it back in. Okay, or if I need to do some experimentation and just test some things out, I can create a branch that I can throw away later. There's a lot of really good benefits when you have this sort of branching and merging type semantics. Now, in data, the question is, where do you do the branching and the merging? Where are you capturing the different versions of your data? So there's generally three categories of solutions that exist right now for capturing versions of your data. There's file versioning. So basically, this would be with the company LakeFS. So essentially what they do is that they tap into the way S3 compliant object storage works to be able to basically track the versions of your storage. Okay, so essentially a commit would be, hey, you have these files on your storage, and then the next commit will say, hey, we're going to add these files, subtract these files. And you can reconstruct the way your storage looks. And that, because it's focusing on the storage layer and focusing on the files in your storage, it's table format agnostic. So it works with all the table formats, Delta, Iceberg, and Hudi. The only flying the ointment, catches are one, generally like a lot of that branching and merging has to be either done through using their CLI tool or using Python. So it depends on sort of how technical that data consumer is, whether that's going to be easy enough for them to use. But it's also unaware of table semantics. Again, it's just capturing the file layer. And there's pros and cons to that. Again, pro, you can use all the different formats. So if you're using Delta Lake or Hudi, that's really your only versioning option. If you're using Apache Iceberg, well, there's also table level versioning. So the actually now in the Apache Iceberg metadata, you can actually create branching snapshots. So you can sit there and say, hey, the next change of the table, let's do it on a branch instead and isolate those changes to that individual table. Okay, which works pretty well. It doesn't require any kind of tools, extra tools. It's just purely in the metadata. So it's compute agnostic. The downside is it's at the table level. So it's one table at a time. So if, let's say I'm working on 10 tables and I wanted to work on all 10 of them in an isolated manner, I would have to create a separate branch in each table. And then I would go back and then merge each one all 10 times. And then again, imagine it was 100 tables, 200 tables, it can get a little tedious. Then the third category, this is where that other project I mentioned, Nessie, comes in. There's catalog level versioning. Okay, and this is done through that open source project, Nessie. What Nessie does is that it's an Iceberg catalog that captures those references to all your Iceberg tables, but does it at the catalog level, and also allows for branching. Okay, so basically what I can do is I can say, hey, I have these 10 tables, and these are my 10 tables, and then basically if I'm going to change the snapshot, that there's going to be a change and there's going to be an update to the reference for, let's say, table C, and then that'll be a commit, but I can then create a branch. So then the next change happens on the branch, not on the main branch. So my production users don't see the changes I'm making, but it's not across one table, it's across my entire catalog of tables. So instead of me creating 10 different branches, because I'm working with 10 different tables, I create one branch of my catalog, and that's going to capture all the changes to all 10 tables. And then I can publish all the changes to those 10 tables at one time by just doing a merge. Okay, so that's sort of like the difference. With table and catalog versioning, you do have SQL semantics, so literally all of it can be done through SQL. Because you're working with a table level abstraction, which allows you to express it in SQL pretty easily, because SQL is really built around expressing operations on tables. So that's another sort of differences you see between the formats. Okay, then there's partitioning. The way each one handles partitioning is very different. Okay, this is going to be one of those places where sort of like the decisions in their architecture really made a difference. So with Iceberg, because of the way it's architected, it was able to solve two problems. Okay, so the first problem is generally when you partition a table, okay, just to make sure everyone's on the same page, when I say partition, the idea is that, hey, when we physically add data to this table, we're going to physically separate certain data based on the value of a particular column. So again, if we say, hey, we're partitioning data by timestamp, let's say by month, then each month is going to be written to separately physical files. Okay, so you won't see the data from two different months within the same set of Parquet files. So they're physically segregating the data, not just sorting it. They're going to be in completely separate data files. Okay, now the way partitioning traditionally worked with Hive, because Hive was like the standard that everyone was moving from when they moved to these formats. With Hive, what you would have to do is that you need to partition based on a particular column. But what if you want to do it based on a timestamp? The problem is a timestamp might be capturing milliseconds or nanoseconds. You're not going to create a whole separate data file for data coming in each nanosecond. That would be, you'd create so many small files that your queries would be super, super slow, having to open up all those files. So what you would do is that you would have to, if you're the data engineer, every time I ingest that data, I'd have to make sure I add an additional column where I convert that timestamp into like a value for the month. So it'd be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 or something like that. So I would mean I have to do extra work when I ingest the data. So that way there's this extra column for me to partition on. But that would also increase the amount of data I'm storing, because now I'm storing that extra column of data for each record. And then for the data analyst and data scientist, now when they query the data, their SQL not only had to say, hey, I'm looking for data within this timestamp to this timestamp, but if they did that, they'd still scan every file because it's not partitioned on the timestamp. It's partitioned on that extra month column. So I'd have to add another predicate to my query saying, query all data between month 5 and month 8. Okay. And that's not necessarily very intuitive or very natural. So this is like extra work that the engineer has to do and extra work that the analyst has to do. So what Iceberg did is that it said, let's not do that. So what it does, it tracks partitioning based on transforms. So you can say, hey, I want to partition this table based on a transformation to month on the timestamp column, and that's tracked in the metadata, not in the actual data itself. So there would be no extra month column in the data files. Instead, in the metadata, it would just say, hey, the way this is partitioned is this column applying a month transform, and then the query engine would know, okay, transform that timestamp into a month value when it's reading the ranges in the metadata. Okay, so it allows it where basically the engineer doesn't have to do all that extra work of constantly converting the data to an additional column, and nor does it have to store that data. And now when the analyst writes their query, if they say, hey, can I query the data between this timestamp and that timestamp? That's automatically going to be picked up by the metadata because it knows, hey, that's the timestamp column that we're doing this month transform on. Let's make sure we apply partition pruning. Let's make a smarter query plan. So basically makes using partitioning and a lot easier. But again, that's strictly to just sort of like its architectural approach to how it handles its metadata, because the metadata, all that stuff is tracked in sort of one central place, that metadata.json. But not only that's what's referred to as hidden partitioning. But not only that, you could actually evolve the partition. What if you want to change how the table is partitioned? So let's say you're partitioning the data by month, and then later on you want to partition it by day because you're getting more and more data. Traditionally, and even with Delta Lake and Hudi, if you wanted to change the way the table is partitioned, you have to rewrite the table. So if you have petabytes of data, guess what? All of that's being rewritten. And if you're a Netflix and, basically, hey, more and more movies are coming out, more and more shows are coming out, more and more views are coming in, so now I need to partition that data more granularly, you don't have to rewrite all your previous data just so you can better partition your future data. So Iceberg allows you to do partition evolution. And again, it's because all that's centralized in the metadata.json, it doesn't interfere with the other parts of the planning process. Now, Delta Lake does not have partition evolution. And part of the reason why it can't is because the changes basically what happens is that the partitioning is identified at the very beginning of the process. So what would happen is that, and any changes to the table structure are documented in those Delta log files. So the problem is if I'm going through each Delta log file and pruning files as I go, and I get to the 10th file, and then suddenly the partition changed, well, theoretically, then we either have to go back and redo the planning of the first 10 files, which really isn't practical. So that really doesn't quite work. So basically, because it's fundamental structure, it kind of precludes that particular feature. So what they did instead is they created a feature called generated columns. But generated columns isn't the metadata feature. So it isn't the function of the metadata, it's a function of compute. So essentially the idea here is that, and I still think this feature might still be Databricks only. Essentially what you can do is you can specify that a particular column has a relationship to another column. So in this case, you could specify that month transformation. And so every time you ingest data, instead of you having to write that logic to add this extra column, Databricks will just do it for you. So you're still storing the extra column, but you don't have to do the work to do it. And if you're the analyst doing the query and you say, hey, let me query the data between this timestamp and this timestamp, Databricks knows that, hey, you generated a column based on that and you're partitioning based on that generated column. So it'll automatically transpose that additional predicate in the query. So essentially it's automatically doing the work for you. But again, it's not a function of the metadata. It's a function of the particular tool you're using, in this case, the Databricks version of Spark, being aware that you did that, and it's being registered in the way they kind of hold the data in their platform. Okay, and then Hudi, they don't have a feature like that. You can partition the table in Hudi and take advantage of the speed of partitioning. But the idea is that they have the metadata table with the stats of each file, the column stats index, and to them, like, that's going to be good enough to be able to prune the files from your query, that you don't need partition evolution. Now, that's just the take there. Cool. But at the end of the day, there's going to be reasons why people might use all three formats. Okay, people like Databricks. Okay, so people might still want to do a lot of their AI/ML on Databricks using those notebooks with those really easily to spin up Spark clusters, and or using the Photon, which is like their basically they rewrote Spark in Rust, and that's what the Photon engine is. So you might want to use that, and that's typically generally a lot of Databricks is going to be very Delta Lake centric because that's their format. Okay, and they generally want people to use that because it does make their platform very sticky because your data is now in their format. Even though other tools can read Delta Lake, don't get me wrong. But again, a lot of the best features are going to be Databricks only. A lot of the optimization and management is going to be housed within that platform. But you might want to use AI to AI/ML there. You might want to use Hudi for streaming. So some people might decide, hey, I really like using Hudi for streaming. It beats my particular SLAs, so I'd rather stream the data directly into Hudi. But they may, and I think this is the direction where a lot of people are going, is saying, hey, the girth of my data is going to be an Iceberg, because that's going to be the format that works with the most tools, and it has the most sort of general use case type structure. Like its architecture is very much more like not for a particular platform or for a particular use case, but very sort of general use. So that basically it's pretty good for 90% of the things you're doing. Okay, so you're generally going to be in a good spot most of the time with Iceberg. So a lot of people are saying, hey, that's going to be where I default. That's going to be sort of where my data gravity is, but I might have some Delta Lake because of my AI/ML workloads in certain departments. I might have some Hudi to handle some streaming. How do I make all that work together? Okay, and there's a couple different approaches to how do you do this interoperability between these formats. Okay, which again, over time is going to become less and less of a matter. Like I'll talk about a couple cool things that are coming up that might really change this. But you could use a lakehouse engine that supports multiple formats. Like Dremio supports Delta Lake and Apache Iceberg. So if you have you have a Delta Lake table you wrote with Databricks, but then you also have Apache Iceberg tables that you wrote with Dremio or other tools, you can join them together. You can actually even connect to your Snowflake and then join that with your Delta Lake and Iceberg tables. There's one house came out with a thing called One Table. It's no longer called One Table. They've contributed to Apache, and it's now called Apache X Table. But essentially, it's a tool for converting the metadata. So what it does, it just converts the metadata from one format to another. Right now, I think it's more of like a one-way, one-time kind of deal. So you're basically good for migration. Although I think they are working on incremental features so that we could set it up to be able to incrementally make those updates. So you can go capture the difference between that. The eventual sort of apex will be that you could then set it to automatically just keep multiple tables in different formats in sync. Delta, like basically in the same way that the Iceberg sort of momentum really started becoming like a thing, and it got really visible. So that's why you're starting to see a lot of these projects. So like the Apache Hudi community, like their response, because One Table is the company One House is the company founded by the creators of Hudi. Their response is, okay, we need interoperability. They created Apache X Table. The Delta Lake, Databricks, their response was to create uniformat. Okay, so it's like, okay, well, there's people who want to use Iceberg, fine, but we still want to, Databricks world, still Delta Lake world. So we're going to let you use your Delta Lake tables as Iceberg tables. So when this uniformat came out, what it did is that you could write to Delta Lake just like you normally would using Databricks. And if you're using their Unity catalog, you can enable this feature. So still, again, a Databricks-centric feature. And it will automatically create Iceberg metadata. So it'll create two sets of metadata, the Delta Lake metadata and the Iceberg metadata. They're not necessarily always perfectly in sync. There's some catches and some caveats to that. And then certain features, if you use in Delta Lake, then precludes your ability to do this. So it's not perfect, but they do that. And then what they do is they expose a Iceberg catalog for you to be able to connect to the Iceberg version of it. So if you have a tool that only connects to Iceberg, you could theoretically still run that against that data. They just added Hudi support, I think like a couple weeks ago, and that technically they actually used Apache X Table to add that. So basically now these projects are starting to all intermingle. Okay, so that's I think that's like the last slide of this presentation. Oh, and again, just a reminder, like if you want to learn more about Apache Iceberg specifically, I wrote a whole book on it. I'm one of the authors of this O'Reilly Apache Iceberg the Definitive Guidebook. So I spent a lot of time reading a lot of docs, a lot of code to put this thing together. Lots of fun times. And then also, again, a really good platform. Like I mentioned Dremio and how we're like a lakehouse platform. And actually, and I mentioned how you could actually deploy it really like on-prem. So you could literally deploy it on your laptop. So if you really want to get hands-on and see like end-to-end what a data lakehouse looks like, there's this exercise you can on this QR code that's right here on the left. That's an end-to-end exercise you can do completely from your laptop. So no need for like having to go get a cloud account. No need to basically zero cost, completely done for your laptop. You get to see Dremio, you get to see Nessie, you get to see Minio, acting as your data lake in this situation, and actually literally create a full functioning data lake on your laptop. So you can see how easy a data lake can be and how much it really does feel like you're using a data warehouse, but with your data lake. And that's going to be the QR code on the left. Then I created a whole bunch of new tutorials, which I think is the next slide, right here, that take that idea and expand it. So these tutorials will actually take you from a data source all the way to the BI dashboard. So in this case, in each of these, you start off with a database, so either Postgres, SQL Server, or Mongo. You'll see it, and this is all on your laptop. So again, no cloud services. This is all be done locally for free. You're gonna seed some data in there, then you're gonna connect the database to Dremio, ingest the data into Iceberg tables, and then build a dashboard with the Apache superset. And you see how literally you can, like, within 30 minutes, you've just done the end-to-end data engineering and data analyst story in one fell swoop. It's a real good proof of concept, so you can see, hey, like, what is this in action? What does this look like? What does it feel like? So I highly recommend trying one of those out, depending on which database you probably use more often. Scan that one. So if you use a lot of SQL Server, do the SQL Server version. If you use a lot of Postgres, use the Postgres version. If you use a lot of Mongo, do the Mongo version. It's generally the same exercise, but just with the tools that you're more used to. And there'll be more versions of that coming out after Subsurface. And again, make sure to follow me, bio.alexmerced.com/data. That has links to everything, all my podcasts, the book, the blogs, all the things. And that's the end of the presentation. I'll just make one more footnote, just like looking forward to Apache Iceberg. And again, all this stuff will also have a lot of talks covering at Subsurface next week. So do register. But one of the interesting things is that Apache Iceberg now not only has like this open table specification, but it's created a open catalog specification. But the catalog specification, again, the difference between what it is, it's not the actual how to make a catalog. It's a standard REST API. So it's a REST API specification for anyone who builds a catalog. So like a Nessie or any of the other catalogs that exist, they can implement this REST spec. So the idea creates one connector that can connect all the catalogs. So any catalog. And one of the things they're doing to change that specification is they're doing what's called the scan planning thing. So basically what's going to happen is in the future, instead of a query engine going to the catalog, finding the metadata, and the query engine is doing all the planning of the scans, to be able to optionally offload it to the catalog. So if a catalog wants, you can say, hey, you know what, tell the engine, be like, no, you don't do the planning, I'll do the planning. And the cool thing about that is that if the catalog does the planning, it doesn't then technically the query engine doesn't care what the format is. Okay, so then theoretically you could create a catalog. So again, this is probably a couple years off, but theoretically you could have a catalog of tables, and since the catalog does the planning, the catalog could theoretically track Delta Lake tables, Apache Hudi tables, Apache Iceberg tables, because as long as a catalog knows how to read the metadata, it can do the planning and then just send over to, let's say, Dremio or whatever query engine the list of files that were part of the plan, and then that's it. So again, Apache Iceberg is really starting to release some of the pieces that in the future could really unify everything if they're implemented right and taken advantage of right. So it's really interesting space. And yeah, we're trying to peek into what the tomorrow will look like. There's a lot of interesting stuff going on here, but I'm going to open it up for Q&A. So feel free to ask me any questions you want. I love to provide answers.
Awesome. This was awesome. Thank you so much, Alex. And everyone, please go off mute if you want to ask any questions, and turn on the cameras if you want to. I want to try this. So the version that you said before that you could install, is it the one called Dremio Community Edition? Is that the one?
Yeah. Yep. You can just do it with Docker. So if you follow one of my tutorials, it'll literally walk you through all the steps of setting it up.
Right.
So you basically just copy some commands into a Docker Compose file, and literally it'll spin up Postgres for you. It'll spin up Dremio, Nessie, Minio. Everything will just be up in a few moments. Awesome. And then you can experience it all. And then it'll be up. I have a bunch more coming out like that. Basically, I'm finding Docker Compose a really nice way to create easy to do tutorials. So that way you can really kind of get hands-on with it.
Awesome.
Cool. But barring, I'll give it another moment for questions. Wait, let me take a look at the chat to see if there's any questions in the chat. Where's the chat? Oh, there it is.
Shamika is registered for the subsurface. Yes, she can't wait.
Cool. But otherwise, everybody make sure to add me on LinkedIn. Always glad to take questions anytime. I'm also posting a lot of content on LinkedIn, blogs, videos, all sorts of stuff. So if you found the space interesting, I definitely will keep you up to date on it. And again, Cecilia, thank you so much for having me on here today. And lovely to see you again. And thank you so much.